Our next question is from GATE 2016 heat transfer for 2 marks. The question is, in a 1-1 shell and tube heat exchanger, steam is condensing in a shell side at a temperature of this, and the cold fluid is heated from the temperature of this to temperature this. The energy balance of equation for this heat exchanger is this. The U is the overall heat transfer coefficient, A is the heat transfer area, M is the mass flow rate of the cold fluid, and Cp is the specific heat. Tube side fluid is in turbulent flow, and the heat transfer coefficient can be estimated from the following equation. Right? Nusselt number is equal to 0.023, Reynolds to the power 0.8, and Prandtl to the power 1/3. This is the Dittus-Boelter equation, where N is the Nusselt number, R is the Reynolds number, PR is the Prandtl number. The considering heat transfer coefficient in the shell side is significantly higher than the tube side heat transfer coefficient. The resistance of the wall to heat transfer is negligible. If only the mass flow rate of the cold fluid is doubled, what is the outlet temperature of the cold fluid at steady state is? Let's start with the solution. You can see here we have given this equation, right? Since we are not changing the area, we are not changing the specific heat. Since specific heat is a constant, area is also constant, so we can say it is a directly proportional of U upon M only. Why I am doing this, you can see in further slides. Since we have given the Nusselt number, we have given this, Nusselt number is this, so we can do one thing. We can say, since why I am writing it, Nusselt number is directly proportional to the Reynolds to the power 0.8. I am just taking this only. Why? Since Prandtl number will be constant. Prandtl number is a Cp mu by K. Viscosity will be constant. K thermal conductivity of the liquid will be constant. Cp of the specific heat will be remain constant. So Prandtl number will remain constant. But here Reynolds number will change. Why it will change? Since you can see here we are just doubling the mass flow rate. If we double the mass flow rate, then the velocity will also increase. Since Reynolds number is given as dV rho by mu, so when velocity will change, then Nusselt number will change. So only Nusselt number will depend in this question is only on the Reynolds number. So I am writing here Nusselt number is directly proportional to Reynolds to the power 0.8. And you know that Nusselt number is given as HL by K, yeah, right, or HD by K. K is where H is the heat transfer coefficient and K is the thermal conductivity of the fluid, and D is the characteristic length, or you can say diameter of the pipe in case of the pipe, right? So here H will depend on the velocity, H will depend on the Reynolds number, since other things are constant. So here from here we are getting H is only directly proportional to the Reynolds to the power 0.8 again. And H can be written as Reynolds number can be written as dV rho by mu, and mass flow rate of the fluid is given as density into area into velocity. Density into area of the pipe, and V is the velocity. From this we can write it as rho V is equal to M upon A. So we will put this rho V is equal to M by A in this, so we will get dm upon A rho to the power 0.8, right? So from here we are getting, since D is again constant, area is again constant, viscosity is also constant, so H is directly proportional to only M to the power 0.8 here, right? Since you know that U is the overall heat transfer coefficient they have given, and H is also heat transfer coefficient actually, right? And U is the overall heat transfer coefficient which consider conductive heat transfer and convective heat transfer. But here when fluid flow is increases, the convective heat transfer coefficient will increase, right? So U will increase with H. So instead of H we can write it as U is directly proportional to the M to the power 0.8. There is no problem with this, right? Now you know that I am writing initially, I have written initially that ln is directly proportional to U upon M, right? Instead of M I can write it as M to the power 0.8, right? Finally I can write it as this is directly proportional to the M to the power minus 0.2. Again they have given initial condition. Initially they have given that Ts we have T1 given, we have given the temperature T2 90 degrees centigrade, but they are asking the temperature T2 in case of that when mass flow rate will be doubled. If only the mass flow rate of the cold fluid is double, what is the outlet temperature? Means T2. They are asking T2 in new case. So we will see. I have put the values, you can see here, in first case, in then I got this. In second case, ln Ts minus T1, Ts will remain same, T1 will remain same, right? But T2 dash will change. Then T2 dash is directly proportional to M dash is equal to minus 0.2. Now you can see here, I will put all the values, right? And we know that M dash is equal to 2M, since we are doubling the mass flow rate. If we are doubling the mass flow rate, then we get this, right? If we divide both equations, then we get ln of this, right? This. After solving, I got T2 dash is equal to 84.18 degrees centigrade. This is the final answer. So thank you. Please make sure to like, share and subscribe my channel. Thank you.